Good morning. We will talk about a new topic. So till now we have been discussing about the analysis of stress. Now, as a mechanical engineer, there are two things we are supposed to do. One is to manufacture or produce some machine, and second is to design. And essential part of design is to understand what are the different modes in which a particular machine or device that you are trying to make will fail. So there are two modes of failure. One is the mode where the equipment will break. There will be some crack will be joined into it, it will get welded, there will be some plastic deformation. So that is the area what we have been studied till now, that is the stress analysis, where you calculate stress or the internal resistance of the body and compare with the material permissible limit, that may be yield strength, ultimate strength. That is one approach. Another important approach is where we not only want the body to get broken, but we don't want it either to get excessively elongated also. So we want certain kind of rigidity in a particular body. So can you think of some applications where the deflection, deformation, rigidity is an important aspect? Which cases you think deflection will be important? Either having certain deflection is important or restricting the deflection may be important. So some parts by design may require to have flexibility and some parts by design may require to have rigidity. So think of some application in terms of flexible devices and something in terms of rigid devices. Spring is an example where the deflection is important. So in the spring you essentially want to control that you should have a certain amount of deflection without having the failure. So there the criteria for design is the deflection rather than stress. Of course you don't want spring to break, but for a given force how much it should deflect, that is important for the spring. Any other That's right. They have to be rigid. What happens if they are flexible? It will not collapse the structure. That is the bending which will occur. So what is the effect that will be there on the users of the bridge, the cars which are moving on the bridge? What will have? It will have. That's right. It will have movement or will have a vibration when you are moving on such a bridge. You will feel risky. Nobody will try to drive on such a bridge. So similar thing will be there for the machines as well. So if you go to the machines or the lathe machines that you are using in our workshop, you find certain kind of construction. If you go to a fabrication shop whose job is to produce a quality machine part, you will not find the machines as flimsy. In the sense, these machines are only for light work. So they are made with light frame, with everything which is bare minimum required. Of course, they are not very flexible. But if you try to make some accurate machining on them, it will fail. Because the machine body itself will start shaking if you want to do some precision work on them. So the precision machines will require more rigidity and such applications. So there are, whenever you have to deal with deflection or deformation, you have to deal with displacement solution of the body rather than the stress solution. So that comes under the purview of the strain analysis, and that is what we will initiate in today's class. So what we are looking here is some body, and it is subjected to some kind of loading. Under the action of this loading, the body deforms and you get a deformed shape of this particular body. So under deformation, each point of this body is taking different points. So any point P you consider here, it will have displacement. For the convenience of understanding, we always express the displacement in the coordinate axis. So you choose some coordinate axis and you will get at every point of this body, there will be some displacement in x direction, which we are calling ux, another deflection in y direction, that is ui, and third one in UZ. So if you, for this entire body, you can write the deformation as U bar equal to UX I bar plus UI J bar plus UZ K bar, where UX is the, at any point, if you take, so any coordinate x, y, z you take, you will get the value, some function would be there that will give you the UX deformation. So to understand this, let's take one simple case. We are considering a bar which is subjected to some force F. The bar is having length L, and because of this force, this bar is deforming by distance delta. It is held rigidly at the left side and it is getting pulled under the force F. The deformation is given as delta. Okay, so this is our coordinate system. So this is x, this is y, and this is z. And let's say our point of interest is P. So what is the deformation? What is the ux, uy, uz at P? Ux, uy, uz at P, how much it would be? So ux is the deformation in the x direction at point P. So how much is that? This bar is elongating by delta. So how much will be displacement of u, the point P? Yeah, delta in the vector form. Okay, so magnitude will be equal to delta. What is the deformation in y direction? In this direction? That would be 0. That 0 comes under some assumption. So anybody can tell out this assumption? Will there be some? Yeah, that's right. So what will happen to the height of this bar when you pull it? It decreases. What is that effect called? So there is some material property which determines how much it will get laterally contracted. So that is called as a Poisson's ratio. You must have learned it and forgotten it. But that is what we are ignoring here. If you are considering at the central point, there will not be any UI. If you consider anywhere else, the UI would be there. But for simplicity, we consider that Poisson effect is neglected. Similarly, in the z direction, perpendicular to both direction, the bar will contract, but we are ignoring that, so uz will also become 0. Now, if you have to write for this entire bar, that is this entire object, what is the displacement field, u bar? So for this bar, if you take any arbitrary point, so if I take any arbitrary point q, and if you ignore the Poisson effect, what would be the value of ui and uz? You are simply pulling the bar. So will there be vertical deformation or transverse deformation? So there will not be any transverse deformation. So for this particular case, the uy would be 0 and uz also will be 0. Now ux will change as x changes. So x equal to 0 here, and at this point x equal to L. So can somebody tell what would be this ux function for this particular problem? So when x equal to 0, the deformation is 0. When x equal to L, the deformation is delta. So in between, from x between 0 to L, you have to tell what will be the value of the deformation, that is the ux. Will it be a linear function or non-linear function? We expect it to be linear. If you stretch a bar, if this endpoint moves by delta, what will be the deformation at the midpoint, at the middle length? At the half the length, how much? If you take the midpoint, how much you guess would be this deformation? You can actually calculate, but what would be this value? It will be delta by 2. It is linearly proportional. That's what he said. That's correct. So, in general, can you write what will be the value of ux in terms of x? Delta x by L. That's right. So, you will have the ux for this particular problem. It will be delta by L times x. So, when x equal to 0, the ux is 0. When x equal to L, the ux is equal to delta, and any point in between it will be proportionate. So for this particular problem we get u bar, that is the displacement field for this particular problem, is delta by L times x I bar, and the remaining things are 0. So there is no uy term, no uz term, because this particular under the loading what is given, the uy and uz don't exist. So in general, for many of the routine problems, you can get the deformation field in a body, and from that you have to calculate the strains, and further the analysis can be done, and from strain the stress is to be calculated. This is the typical route that will be followed in what in future semester we learn in the finite element method. So in the formulation of this finite element method is such that first you get the displacement solution. So displacement solution means you will get this displacement field. So anywhere in this body, if you tell the coordinate, you will know what is the deformation. So from the deformation, the next step is to calculate strain, and from strain you calculate stress. So that is how the numerical method or the finite element based method works. So here you will learn, given the displacement field, how do you calculate strain from that. So that is what is the next step. So any questions at this point? So let's proceed now. Given a displacement field, how to calculate the strains in a particular body. The elements of that you already know in 2 dimensions. So first we'll consider the 2-dimensional case. So at this point P, I am just considering a particle which is having length equal to dx, height equal to delta y, and this particular body is getting pulled only in x direction. Just like this particular bar, we will consider a situation where this bar is pulled in x direction. So as a result, this particular bar elongates, and the relative elongation of the right face with respect to the left face. So whenever you elongate, this left point is also going to get some ux, right point is also going to get some ux. The difference between them is the net elongation of this particular bar. So let me call this particular as delta ux. So ux is the notation for displacement in x direction. Delta ux is the differential expansion that this particular bar has between its left edge and right edge over the length delta x. So if you consider the relative displacement, here the displacement is 0 and the displacement of right side is given by delta ux. So this much displacement occurs over the distance of delta x. So our classical definition of strain, what is the classical definition of strain? How strain is defined? Change in length divided by the original length. So if you apply that particular definition, we can give, so this is the x direction, this is the y direction, and we are considering 2D scenario. So we will get the letter which we use for strain is epsilon. So in this course we will be using epsilon for denoting the strain, which you will find in most of the books. So the epsilon x would be given as change in length. So what is the change in length here? It is delta ux. So this particular rectangle is changing by delta ux. And what is the original length? That is delta x as given here. So as this particle size becomes smaller and smaller, this particular ratio will take form of a differential of ux. So limiting case, while x tends to 0, you will get this as dux by x. So if you know the x displacement, the displacement field in x direction, you can calculate the strain by simply differentiating the displacement field. So let's try to apply it to this problem. So in this case, the displacement field is given as u bar equal to delta by L multiplied by x. So here ux is this delta by L multiplied by x. If you differentiate with this with respect to x, what do you get? Delta by L. And what is our classical definition for this problem? The strain is that elongation divided by original length. So that is delta by L. And one more thing, this is a constant. That means any point you calculate the strain, it would be same. So that is what it is. So till now you are imagining strain only at the free end. Now you come to know that anywhere for this problem, the strain remains same, and that is given by delta by L. In this case, and in general, any body whose displacement field is known, the linear strain is given by this particular definition. So these are called as a linear strain. Similarly, you can have in the x direction, in y direction. In general, the ux, that is the displacement field, ux, u and uz, they are not pure function of x. Like in this case, it is pure function of x. But they can be function of x, y, z. So depending on which point you are considering, the displacement would be different. So one simple example would be a bar which is subjected to bending moment. So in this case, the deformation would be depending not only on x but also on y, which location we are considering. So that is why instead of considering the pure differential here, it is written in terms of the partial differential. So here dA by ux by dA by x. So that is the partial differential of displacement field in x direction with respect to the linear dimension in which you are talking. So epsilon x will be given as dA by ux by dA by x. Similar way, in the y direction, you will have epsilon y equal to dA by uy divided by dA by y, and epsilon z will be dA by uz by dA by z. So that is, in similar phase, you just draw the same figure in y direction, z direction. So for y, it would be, if this is the original length, this is delta y, and you are elongating, so this is delta uy. So in this case, you will get this figure, and epsilon z would be given in this particular terms. So these particular terms are called as linear strains. There are other type of deformations which lead not to the elongation of the body, but distortion of the body. So in this case, you are getting some finite change in the length of the body. There are other types of deformations where there is no change in the net, there is no elongation of the body, but the body just gets distorted. So those are classified as the shear strains. So in shear strain, you will not have this elongation, but you will have distortion or change in angle, and that is what is defined for the shear strain. So let's now try to define the shear strain in terms of the displacement field. So here let's understand the concept of shear strain is more complicated than the linear strains where it is simple ratio of elongations. The shear strains are measured in terms of change in the angle. So if you consider an original square piece or two faces which are perpendicular to each other, after the application of load, those two perpendicular faces will come either close to each other or they will move away from each other. So there is no elongation of this face length. So this face length doesn't elongate. It only turns about with respect to each other. And the shear strain is measured in terms of what is that change in angle from the original perpendicular shape to the final shape. So the shear strain which is denoted by symbol gamma. So it is denoted by symbol gamma. So let's call this as X and this is Y. So here the linear strains are denoted by epsilon, the shear strains are denoted by symbol gamma. So this gamma is nothing but the net angle through which the original perpendicular faces are getting rotated under the application of loading. So in this case the face number 1 is getting rotated by theta 1 and face number 2 is getting rotated by theta 2. So this shear strain would be given as theta 1 plus theta 2. It is just, both these strains are dimensionless, but in case of shear strain, it has got physical meaning that it is an angle in radians, so that is what is the definition of the shear strain. So what our job is to express this theta 1 and theta 2 in terms of the relative displacement of these edges. So let's say that this particular, under the action of loading, this particular edge, it moves by certain distance. So this is y direction. So I will call this as change in displacement in y direction. So this edge, which was originally at, let's say, y equal to 0, it gets lifted up by amount which is delta uy. Similarly, the top edge also gets elongated. Not elongated, it gets displaced by the same amount which is delta uy. Similarly, the second edge, it gets displaced in the x direction. So originally it was vertical. Under the action of loading, it has displaced in x direction. So this I will call as delta ux. So displacement in x direction, and from original vertical to the final is given as delta ux. Now we can write these angles theta 1 and theta 2 in terms of the trigonometry that you see in this particular figure. So can you tell how do we get the value of theta 1 or the trigonometric relation for theta 1? So tan, I listen somebody murmuring tan of theta 1. So okay, that's correct. So tan of theta 1 we can write. So what is tan of theta 1? Delta u by delta x. And tan theta 2, tan of theta 2. So it is the delta ux divided by delta y. Okay, so at this stage we got the tangent of these angles. We did not get the actual angles which are required for our strain definition. So does anybody knows what is the approximation between tan theta 1 and theta 1? So under some circumstances you can relate theta 1 and tan of theta, tan of theta and tan of theta. So angle is very small, tan theta as well as the sine theta, both can be approximated equal to theta. So that is approximation. So the whole theory that we are using here, that is called as a small strain theory. So here all the strains and all the displacement that we are talking about are small. What do you mean by small is that the values of this displacement are small with respect to dimensions. So for example, if you are talking about this bar, when we are talking about small displacement theory, this delta should be sufficiently small with respect to L. So it should be 1% or half percent of L. So there is no hard and fast rule, it should be 1.5%. But it should be sufficiently small, only then you can go ahead. So the formulations that we are developing here, so they are called as a small strain theory. There is another theory which is depending on large strains. So that is outside scope of this work. Most of the engineering problems can be tackled with the help of small strain theory, because usually as an engineer, except when you are dealing with springs and other flexible elements, we want the deformation to be very, very small. So that is usual requirement. So under this scenario, this tan theta 1 would be approximately equal to theta 1 and this would be approximately equal to theta 2. So we got the expression here for tan theta 1 and tan theta 2. The shear strain is always related to two phases. So here we are considering two phases. One is, this is the y phase and this is the x phase. So the shear strain is never, unlike here, it is never related to single dimension or single direction. It is always related to two planes. So that means two directions. So the shear strain is subscripted with respect to the planes to which it belongs. So it is given as xy. So that is what in the stress you will remember. Similar in the strains, the shear strains are related to the plane in which you are calculating change in angle. So in this case we are calculating change in angle in xy plane. So the subscript of this particular shear strain would be given as gamma xy. And that would be given as delta theta, that is theta 1 plus theta 2, which now we can write as delta uy by delta x plus delta ux1 delta y. So just like we did for this element becoming sufficiently small, these ratios can be written in terms of partial derivatives of this particular element. So we can write gamma xy, that is shear strain in xy plane, as gamma ux by gamma y plus gamma uy by gamma x. So if you know the displacement field, you can calculate the shear strain by using this particular equation. So it is easier to remember. So whatever are the subscripts, you have to prove the displacement. So it is always sum of two partial derivatives. So first one corresponds to the first subscript, second to second subscript, and the denominators, they become reverse. So unlike here where it was ux by x, here it is x by y and y by x. So that is the relationship. So similarly the other three can be written. So you can have gamma yz, which is the shear strain as measured in yz plane. So can somebody tell what this would be? So dabba u, what should come here? So it is xy, you have xy there. So it will be y. You can write z also first, but better to go in the same sequence. So dabba uy by dabba z, the other subscript you have to write here. And here dabba u by dabba y. So this shear strain three equations plus our linear strain equation, so that is dabba ux by dabba x. So all these three together, they are called as They are called as Cauchy's strain displacement relation. So what it does, if you know the displacement field, so you know how the body deforms at every point, so you get the total displacement field. Using these equations, at any point in this body, now you can calculate what is the value of strain. And just like stress, the strain is also tensor, and for its full definition, so at a point if you want to define what is the strain, you have to define 3 linear strains and 3 shear strains. So those are the 6 components. Since it is a tensor of second order, we require 9 components. So just like stress, you can represent it in matrix form, so that we'll see a little later. But these are the corresponding to the 6 unique components in the stress tensor. So instead of sigma x, we have epsilon x. So sigma x, sigma y, sigma z. Epsilon x, here we have epsilon x, epsilon y, epsilon z. What is the corresponding terms to shear strains in the stress domain? Tau. So instead of tau xy, you have gamma xy and so on. So that is how this particular strain tensor works. Forgetting tensor, the utility of this is if you know what is how the particular body is deflecting. So if you put, for example, this particular table, you put dial gauges and measure at every point in x direction. Before putting load, you measure the dial gauge readings at various points in this table. And after putting, let's say somebody stands here and you put again dial gauges at various points, you will get every point what is the XYZ displacement at the various points of this table. So once you know this displacement field, using this relationship, you can calculate what is the strain at any point of this particular table. So that is the utility. That is how it gets used in the finite element method. First you obtain the displacement solution, and then from that you calculate strain using the Cauchy's relations. And once you get the strain, use the relationship between stress and strain. That is what we are going to study next. But you already are aware the basic rule is the Hooke's law. From that from strain you can calculate stress. So general direction of analysis would be first get the displacements either experimentally or through some numerical method. Then from that calculate the strains, and from strain you calculate the stress. So that is how a general routine numerical methods would work, and that is what is the utility of this particular equation. So at the end of this lecture we will solve one numerical problem. Before that we will consider some other relationships related to the strain analysis. So any questions at this point? So let's proceed. So there is one relationship which will be used for further strain analysis. So that is, if you know the strain at point P in terms of the 6 components which are given here, and you would like to know, so you have some point in the table and you know what is the strain at this particular strain components at a particular point, and for some reason you would like to know along some arbitrary direction what is, if you put a small rod or consider a small length inside the table along a particular direction, how much will be elongation of that particular rod. It is essentially used to develop the equation for what is called as a principal strains. One would be generally interested in finding out which is the direction in which the elongation is maximum. So as an engineer would like to know as a failure criteria, what is the maximum elongation or what is the maximum strain. In order to reach to that point, in order to find the maxima, first you have to write a general equation that any general direction in terms of given strains, what is the linear strain component. So that expression, so this proof we are not covering, so I am just giving it directly. So epsilon PQ is epsilon x nx square Okay, so this particular expression, it has got 6 components, but it is easier to remember. So I have given the first, so the first 3 terms corresponds to the linear strains, the last 3 correspond to the shear strains. So the first term is epsilon x into nx square. So what will be the second term? We have to just look the pattern into ny square and z square. So this is like question in your scholarship exam or now maybe CAT exam, not so simple, but you have to just observe the pattern and then complete it. So what the second series is epsilon xy into nx into ny. So epsilon ny into nz. And last will be nx into nz. So it is easier to remember. You don't have to remember, but even when you are doing calculations, it is just mentally you can note if you are going in the right direction. Okay, the utility of this expression, as I said, is in determining what is called as a principal stresses, in this case the principal strains. So what is principal strain? So the given strain state at a particular point, you can always find a particular direction in which the strain is maximum. So the principal strain, it means that strain is either maximum or minimum. So here we are talking about linear strain. So we would like to know what is that n bar or what is nx, ny, nz along which the strain is maximum, where the strain in any arbitrary direction is given by this particular expression. This entire expression gives you any arbitrary direction. We would like to know where the sigma pq would be maximum. So which direction or which nx, ny, nz will give me sigma pq as the maximum. So the derivation, which again we are not covering, but just the starting state of that derivation is that we are considering the epsilon pq to be maximum. So derivative of this particular epsilon pq with respect to each of the unknowns, that is baba, sigma, nx, this should be 0. So this expression, so if you partially differentiate this with respect to x, nx, ny, nz, you will get 3 equations. And then the last equation is the property of direction cosine, nx square plus ny square plus nz square equal to 1. So using these equations, you can find out the values of principal strains. Interestingly, the final expression we get is very similar. So note that it is not exactly same, but it is very similar to that of the principal stress equation. So before we go that, we will express this particular strain state at a particular point, just like in stress in the matrix form. So that is called as a strain matrix, so that the principal strains are easier to express in terms of matrix rather than regular equations. So first, before going into the expression or equation for the principal strain, we will look at the strain matrix, which is nothing but the strain state at a point or the strain tensor. So in tensor notation, it will be written in terms of epsilon ij or gamma ij, whatever one notation we are using. Just like stress matrix, it has 3 by 3. The diagonal terms are all the linear terms. So similar, where the normal stresses are lying, in this case, the linear strains will lie. So we have epsilon x, epsilon y, and epsilon z along the diagonal, and the shear terms would take the remaining pocket. So can somebody tell what shear strain component will come here? So gamma xy, gamma yz, gamma xz. So it will be gamma xy. So wherever tau xy is there, in this case it will be gamma xy. Here, xz, and here it will be gamma yz. And these are the 6 unique numbers you require to define the strain state. And just like strain matrix, just like stress matrix, this matrix is also symmetric. So you have gamma xy, gamma xz, and gamma yz. So that is the equality of the cross strains in this particular case. Cross shear strains, so that is what we get here. Now, if you remember, the equation for the principal stresses was obtained in terms of roots of a cubic equation. So in this case, exactly same cubic equation lies, and instead of stress invariants I1, I2, I3, here we have strain invariants J1, J2, J3. They are expressed almost similarly to that of the strain matrix. So it is not difficult to, if you remember the strain formulation, strain formulation becomes simple. So for calculating the principal strain, you have to get the roots of cubic equation, which is epsilon cube minus J1 of epsilon square plus J2 of epsilon minus J3 equal to 0. So it is same way, instead of I1, I2, I3, we have here J1, J2, J3. So anybody recollects what is the expression for I1? So yeah, that's right. So instead of sigma x plus sigma y plus sigma z, it will be epsilon x plus epsilon y plus epsilon z. J2 expression is second order. Anybody recollects? Or you can refer to your notes and tell me. I think one batch has done tutorial just yesterday. So it is a product of two terms. Epsilon x into epsilon y plus epsilon y into epsilon z plus epsilon x into epsilon z, and then there are 3 minus terms corresponding to the shear cases. Plus gamma xy square. So this is where the difference comes. So all of you please pay attention here. In the stress equation, the second invariant had tau xy square, where the tau xy was directly picked from here. Now the important difference, or the only difference in case of the strain analysis, is instead of this gamma xy square here, you get here what is called as exy square, where exy equal to half of gamma xy. Okay, so you have minus exy square minus EYZ square minus EXZ square. Here EXY is half gamma XY, EYZ is half gamma YZ, and EXZ is half gamma XY. So this is the common mistake that one would make in exam, or I find at least 10% of you, even after telling this is important, somehow you directly pick from this matrix and then solve the problem. You have to remember that while calculating principal strains, the shear strain terms, only shear strain terms are to be half, the linear strain terms remain the same. We are not going into derivation of that, so luckily you are saved from the complexity of how this has come. But those who are interested, in the book you can go through why this particular thing is there. So the gamma terms, they are called as the shear strains. There is no specific name for these terms, but in solid mechanics book you will always find this particular notation, that is a small e would be reserved for half the shear strains. So they are just called half the shear strength, or they are called nothing, they are simply called as E strain. And similarly, the J3 can now be written in terms of epsilon and E. So it is not in terms of, nowhere in these equations gamma will appear, everywhere small e will appear. So J3 will be epsilon x into epsilon y into epsilon z. What is the next term? So these are 2 times something. So it will be 2 times the product of all shear terms. EXY, EYZ, EXZ. And then we have the remaining terms. So can somebody tell what is the first term?
Epsilon x, EYZ.
Plus or minus?
Minus.
Minus epsilon x,
EYZ.
EYZ. Minus epsilon y into E. If it is x, it is yz. If it is y, it would be x. Minus epsilon z into E y z. So these are the J1, J2, J3. Very similar to that of the stress matrix, with important difference. You have to halve the shear strain terms before calculating these particular numbers. Once you get this, you have to find the roots of this particular equation, and those are the magnitudes of the principal strain. In order to get the direction of the principal strain, we have to use the similar approach. So we have to solve the simultaneous equations. So the equations for direction of the principal strain. You have to solve the 3 simultaneous equations. So in this set of equations, the diagonal terms, so they are the principal strains are nothing but, it is also an eigenvalue problem. So on the diagonal term, you will have the principal strain getting subtracted. So here you will have epsilon x minus epsilon, so that is the principal strain, epsilon y minus epsilon, and epsilon z minus epsilon. And another change with respect to the stress, here the original strain state had got gamma terms, shear strain terms, here it will be E terms, so it will be EXY, EXZ, EYZ. So the approach is similar, except the important things to remember are the E terms, which are coming in this particular formulation. So using this, one can calculate the values of Nx, Ny, Nz corresponding to the value of the principal stress. So whatever roots you have found out, that root you have to subtract from the original strength matrix along the diagonal terms. Solve these equations. So if you, and you have to also use the property Nx square plus Ny square plus Nz square equal to 1, just like we did for the stress, and calculate the value of Nx, Ny, Nz. So as far as numerical problems are concerned, the procedure part for the strain analysis is very, very similar to that of the stress analysis, except that you have to take care of these small EXY terms. Okay, so that is prepares us for the next week. Now next week we are having 2 batches. Tutorials are getting lost. Monday we have afternoon, we have annual day, and Saturday, Friday is holiday, right? Yeah. So next Friday is holiday. So we are losing batch B and batch C. We are losing the tutorial. So if it is possible, can we have the tutorial for batch B and batch C today from 4 to 5? That is the next tutorial. Only for batch B and batch C. Today the batch D will have the tutorial, so they will do the previous tutorial. So batch B and batch C, can they come today for... so you just work out among yourself and let me know by lunchtime. So what is your final decision? Otherwise, somewhere in the next week, either Tuesday, Wednesday, you decide when these 2 batches together can have the tutorial. So before we close, we'll just look into one. Okay, so we'll do the numerical part in the tutorial. So I wanted to solve one numerical problem, but that would take more than 5 minutes. So it will encroach into Professor Yadav's time. Anyway, we'll be solving the numerical problem in the next week's tutorial. So for, if you decide, the batch B and C can have that particular tutorial today from 4 to 5. Okay, so let's, so unless you have any questions, let's stop here.